The overall goal of this project is to build a machine learning model that is able to predict an individual's annual income if it exceeds $50,000. And so far, I have ensured to build a solid foundation covered in previous videos. This includes areas such as dataset exploration, cleaning, analysis, and pre-processing. In the last video, I was able to train my baseline models, and in this video, I am going to be optimizing these models by tuning the hyperparameters using cross-validation. And now, all of these inputs have been introduced and implemented in all of the previous videos except for 3. The first here is JobLib. This library is what I'm going to be using to save my preprocessing pipeline and my models for when I want to deploy this project. The second is PCA. Now, I did not use PCA because the dimension of my dataset is not so high. Also, feature interpretability is something I prioritize so much, and actually this will be difficult if I were to use PCA. Thirdly, I was able to handle multicollinearity very well during my dataset cleaning and preprocessing. So dimensionality reduction is not really needed for me, and any more signs of multicollinearity, my tree-based models such as random forest and XGBoost will handle this well for me. But of course, PCA is something that can still be explored, but I just did not implement it here. And lastly is my grid search cross-validation. So this is the technique that I am going to be using alongside my hyperparameters to tune my models. Let's get right into it. So before we start tuning our models, let's have a little overview from our baseline models, right? It is important to remember that our data set is imbalanced. So the target, which is the income, is made of 2 classes. The first class, which is class 0, this is the negative class. It includes individuals who have an annual income less than or equals to $50,000. This is the $50,000. This is the majority, and it makes about 75.5% of this data set. Now, the second class is the class 1 or the positive class. And this includes individuals that have an annual income greater than $50,000. And this is the minority, making 24.5% of this data set. So it's very, very important to remember this. Now, in the previous video, while I was training my baseline models, I discuss intensively each of these evaluation metrics and what they mean and the questions that each of them answers, right? And then we're able to see how misleading accuracy can be when we are handling imbalanced data like the one that we have here. Now, so far, all of our models had a great reception of our data, which meant that our pre-processing was good. But looking overall, though XGBoost is the best performing model, all of my models here, they struggle with recall. Their recall for the minority class is low, which means that sensitivity is low. So the models are not really sensitive to the minority class, and it is no surprise because with little to no tuning, these models are going to treat all of the features and data points with the same weight, and it's just natural that it's going to be biased to the majority class. So it's important, knowing this while we are tuning our models, that we actually have to let our models know that this data set is imbalanced and it should pay more attention to the minority class. So as much as we want to increase the sensitivity of these models, we also have to make sure that we are maintaining a balance with specificity and precision. So let's get right into it. So similar to my baseline models, I created a reusable function for tuning my models. And now this reusable function here, it automates the entire process of tuning, training, and evaluating my models. Now, what are the inputs of this function? It takes in a defined model, the hyperparameter grid for that model, and then it takes in my training data and my test data. Now, since I don't know upfront which of the hyperparameter combinations will give me the best performance, I will have to define a hyperparameter grid for every model. This is basically a dictionary containing the possible values for each hyperparameter that I want to test. And now this is where grid search cross-validation comes in. It performs a k-fold cross-validation across every possible hyperparameter combination on the training data only, searching for the one that gives the best performance. And now, after identifying the best combination, grid search refits the model on the entire training set, and then the model is evaluated on the test data. Also, we can see here that I set CV equals to 5. This simply means that my training data is going to be split into 5 folds. So training is going to happen on 4 folds and validation on 1. and this is going to be rotated so that every fold has a chance to be used as a validation fold. As we can see here, I also set my scoring metric to be ROC-AUC. I simply did this because I want the model that best separates between the two classes. And this is very important, especially that my data set is in balance, ensuring that, my model is able to generalize well. And then finally, this function evaluates the model on the test set here, and then it calculates the evaluation metrics here, as we can see, and it also prints the results here, also giving me a confusion matrix and ROC curve, finally returning a dictionary of results for my model comparisons. Now let us tune our logistic regression. Here I'm creating my hyperparameter grid. As we can see here, I'm exploring different hyperparameters, including regularization strength, type of regularization, and optimization algorithms. And here are the values that I want to explore. Now, while running this model in my tune and evaluate function, I'm creating an instance of the model here. As we can see, it is important to note that I am including class weight balanced. What this does is that it informs my model that the data set is imbalanced, and so it should pay more attention to the minority class. Now, this is what will really help our recall. Let's look at the result. Now, looking at the accuracy, it is slightly lower than the baseline logistic regression, right? But looking at the recall, there is a high improvement in it. But now our precision drops a lot. So the recall precision trade-off is so much here, and this is not looking so good. Now we can see that the false negative values here have reduced compared to that of the baseline model, but the false positive values here have increased significantly. Our AUC score is 0.89, looking good so far. Now, let's tune our random forest. Again, I am defining my hyperparameter grid. Here are the hyperparameters that I would be tuning. The number of trees in the forest, maximum depth of these trees, and also my split rules. And here are the values that I want to explore. Basically, the values that, grid search cross-validation is going to be using. Now, while running it with my tune and evaluate function, I am creating an instance of the model here. Again, just like we've seen with logistic regression, I am assigning, class weight balance for the same reason, to help my recall. Now, looking at the result, surprisingly, or maybe not really surprisingly, because random forest is known to be really stable because of how it ensembles the decision trees, right? Now, let's look at the accuracy. Accuracy here is slightly higher than the random forest we saw that we trained in the baseline models, right? Now, if we look at the recall and precision trade-off here, the trade-off is not so much. Again, random forest is a quite balanced model, as we can see here. Also, the drop in my precision is not so much. So far, so good. We are seeing great improvement with our random forest. Again, false positive values decreasing, false negative values here decreasing, false positive values increasing. We are seeing the recall precision trade-off here. Our AUC score is 0.91, not bad at all. It's actually good. It means that the model is able to separate between classes very well. And now, tuning my XGBoost. Here are the hyperparameters, and here are the values for the hyperparameters that my grid search is basically going to be using to get the best performing combination for me. Now, before running it, I have to calculate my class weight. Now, XGBoost does not have the class weight hyperparameter like the other models that we've seen. What it has is the scale pos weight, which is the scale positive weight here. Now, but before setting this hyperparameter here, we first have to calculate the scale weight. And what this does here is, just like with the other models, it informs the model that the data set is imbalanced and it should pay more attention to the minority class, which is the positive class. So that's basically what it does. And now, running my XGBoost, again, if you've not noticed with the other models, part of what the function does is that it prints out the values of the hyperparameters combination that gives the best performing model. So for every model, we see the best parameters printed out here. Now, looking at the accuracy of my XGBoost, it is slightly less than the XGBoost in baseline, but not like with much difference, right? Again, looking at the recall precision trade-off, it is not so much here. Now, there's great improvement in my recall, but my precision also dropped a bit. Now, the fact that recall is getting better and it is increasing, what this means is that my models are generally getting better at correctly identifying the positive class. So it is getting better at correctly predicting the individuals that have an annual income of greater than 50K. But here we can see that precision is also decreasing a little bit. It means that at the same time, it is also misclassifying the people in the majority class. But we can see here that the trade-off is not so much here, and if I were to deploy this project, this is the model that I would in fact be using, because so far it is the best performing model. Again, we can see here that the false negative values have decreased significantly, but again the false positive values have increased. So this is the recall precision trade-off that we can see here. Again, our AUC value is 0.93. The closer to 1 it is, the better. So this is really good. It means that our model is able to distinguish between the two classes very well. Another thing I did was to calculate the feature importance for my tuned XGBoost. Now, I did this for the baseline XGBoost, but I'm repeating it. And the reason why I'm doing this is to see if there is a consistency in the features that affect my model's learning the most, right? And now I can see that there's a consistency with the features of with the XGBoost in the baseline models, and also the patterns that I saw in my exploratory data analysis. And simply what this is telling me that tuning the model is improving the efficiency and it is not changing the direction, which is good. It means that the learning of our model is stable, and also the patterns that we saw in our exploratory data analysis are strong and are clear, and that is just a confirmation that we need. So the final model that we are considering here is our support vector machine, and a quick disclaimer is that I used my local computer, so running this tuned support vector machine took over 3 hours to run. So anyone that would like to try this, I advise that you should probably use maybe randomized search cross validation. That should not take as much time as the grid search took, or you just performed the whole project on Google Colab, because the CPU cores there are stronger and are more powerful. So that's just a quick disclaimer. So for our support vector machine, here are the hyperparameters and the values that I'll be exploring. Of course, I'm using class width balance to handle the imbalance situation of my data set. Again, here are the best parameters. Accuracy is looking good so far. This is very, very similar to my random forest, and again, like I said, my models are actually getting better at predicting the positive class. But so far, this is just a general summary, But again, I ensured that I compare my tuned models just like with the baseline models, right? So here I have a combined ROC curve for all of my models. Again, we can just see it showing clearly the performance of these models and how well they are able to classify or differentiate between classes across multiple thresholds. Of course, again, XGBoost is the best performing model. Another thing I did was simply to create a table that compares this performance of my tuned models in one place, so I can just at a glance see all of them. I did the same thing for the baseline models. Also, I compared my baseline models and my tuned models in one place, so we can have a once glance summary of all of this. From everything that we have seen, is like, if we want to improve the imbalance nature of this data set, something that we can do is collect more data for the minority class to help balance it, or we can implement SMOT, which is like a synthetic way of generating more data for the imbalance class. Also, if we want to explore the interpretability of the features of the models, we can implement SHARP for that. And finally, something we can explore is model stacking. We saw how really stable our random forest is. We can decide to stack our random forest and our XGBoost for better performance. So those are some of the recommendations that I can give for a better result of this. Simply what I'm doing here is saving my pre-processing pipeline and all of my models. I would have just saved only my tuned models, but I just decided to save everything. And here is simply the general summary of the project. Also attached to this project is the GitHub link to the entire project, everything that you're seeing here, and also the raw data set. So anyone that is interested, you can check it out.